let me get started. My name is Wu-chang. I teach at Portland State University, and I'm going to talk about this symbolic execution CTF and how. So I want to teach this in my classes, and so we developed this CTF last summer, and a high school student basically did most of this work. So Jake Springer, who's now a freshman at Swarthmore, and so he put together this CTF. And I'm going to step you through it. But first, this is completely hands-on. I want you to be able to run the symbolic execution engine on the binaries that I give you. And I'm going to walk you through how these scripts work. So give you the conceptual sort of understanding of what symbolic execution is, and then step you through how it plays out in the Anger framework programmatically so that you can actually go and apply symbolic execution to any number of binaries you might come across. So in order to do this, in my slide talks, or in my abstract, I had people try and install Anger. There's a Docker container that you can install. You can install it on a VM using a Python package. There's multiple ways you can install it. If you don't have it, I'm recording this video. You can download it after and then play along with the video afterwards if you want to see it. Okay, so those are the URLs. Okay, so symbolic execution. At a high level, so what did the entries in DARPA's recent Cyber Grand Challenge have in common? Well, it turns out two things. They were using smart fuzzers. Do any of you're all familiar with the Cyber Grand Challenge? This was the autonomous hacking thing. So pretty much every system that made it to the finals was using a combination of smart fuzzing and symbolic execution. And so here's the $1 Million Baby talk from Shellfish. They actually placed third, but their system was actually the most sophisticated. I think a lot of people understand that what they pulled off at the CGC had never been done before. And I'll actually play the video of the commentary from this thing. And if you look at what they talked about, and they call it $1 Million Baby because they won basically $1 million. I mean, so I think they have $750,000 in the finals, and then some other money on top of that. So they call it the $1 Million Baby. And they, this is one of the things that they were looking at was to use fuzzing. So this is American Fuzzy Loft is a fuzzer, a smart fuzzer, and we'll talk about what these things are in a second. And then they use Anger, which is their symbolic execution engine. And so, in particular, they used it to automatically exploit something that's called Crackadder. This is a vulnerability found in 2003 it could be boiled down to 50 lines of C code. And what it allowed someone to do is to write an email that basically was able to take complete control at the time of every single email server that was running. And it was a bug in the email parsing. And it was so email parsing has this complex state machine in order to actually parse the message. And so this state machine basically has more atoms than we know in the universe in terms of the number of states it could take on. And so if you do something like static analysis on this thing, because of the path explosion in this code, you can't analyze it for the bug that's in here. And this is the thing that Shellfish exploited automatically. So this is the exploit. So in your email address, you have the greater than bracket and the less than bracket. They're sort of like tags, right? And to figure out your embedding in this parser, you even them out, right? +1 if you get a greater than, -1 if you get a less than, and it descends into this tree. Well, as it turns out, the parentheses wasn't handled correctly. So, and if you did enough end parentheses without enough open parentheses, you could actually get an overflow. But as it turns out, in order to actually exploit that, you needed 65,535 different ones of these. And so by the time you figure out what was vulnerable, you basically have, if you were to fuzz this brute force without any knowledge, this thing would take you 10 to the 65,000 sort of combinations in order to find the one that would exploit this vulnerability. So this is the thing that that Shellfish found via smart fuzzing and symbolic execution. And their frameworks, the smart fuzzer was called Driller. and then obviously anger, which is what we're going to talk about in this workshop. So I think I can play the CGC commentary on this just to give you some context of what we're doing. The details, there's this epic frac post about a description of their entire rig, which is way more than just what we're going to talk about. Okay, so he talked about smart fuzzing and symbolic execution. And the combination of these two techniques, I think, are about to change the way we test and analyze code. I think in about 4 or 5 years from now, this is the way of getting your code analyzed for bugs. These are powerful tools. A lot of the companies that participated in the CGC, they're commercializing their stuff pretty quickly. So what is the power that it gives a user? Well, you can find and exploit latent vulnerabilities in code automatically, like this one did with the crack adder. You're able to test all of your code paths in your programs and through complex programs, right? So if you want to make sure you have a test that exercises every line of your code, you can use smart fuzzing and symbolic execution. If you are a malware analyst and you want to determine whether or not two binaries of metamorphic malware are equivalent, you can use symbolic execution. If you, again for malware, if you see that there's a backdoor in a binary, you can figure out what's the input that triggers that backdoor. So these are really powerful things that if you can get a program to do that automatically, well then you don't have to spend the time to reverse engineer the thing. Okay, so I believe that these are tools that eventually all the students, at least out of Portland State, should have in their toolbox. And so this is something that I'm putting into our malware course at Portland State beginning next quarter. So you'll be test driving some of the binaries that we'll be having our students work on. So first, what is smart fuzzing? So fuzzing has been around for a long time, and it's only recently that fuzzing has made a comeback. And so initially, fuzzing meant black box fuzzing, that you had no idea what that thing does on the inside. What you're going to do is randomly generate input and see if that thing crashes or does something unintended. So that's black box fuzzing, to blindly brute force the input. And it's not extremely efficient, right? Like you have to make sure, 10 to the 65,000 inputs before you can get that, you're never going to get that, right? So it's really hard to exercise every line of the program, and as well as 10 to the 65,000 inputs. So the advance that happened in the mid-2000s was white box fuzzing. And so we consider this smart fuzzing. And the idea here is that if you have your code base, you instrument your code base with a special compiler. So AFL is a special compiler. And what AFL will do is it'll place audit points throughout your code. Every time a branch happens, there's a piece of code there that audits, yeah, that input case hit this particular part of the code. And you can tell with instrumentation, if you're applying inputs on your implementation, and you can see the code paths that get exercised through it, you can tell which inputs will generate code paths that you haven't seen before. And that's the fundamental innovation with smart fuzzing. You can more intelligently fuzz that program if you know the code paths of different tweaks to the input will have in the execution. Okay, so you're intelligently fuzzing based on how close you can get to hitting new code locations in your program. And I think this is going to be the future of automated testing. And one of the things that I'm interested in is a smart fuzzing CTF. And so maybe next year, if we've written one, we'll go through it. But actually, the workshop right after this is on fuzzing, and I'm guessing it's probably AFL fuzz. So maybe we'll just get. Are you doing the AFL? Oh, okay. What are you using something else? Oh, okay. Okay. Great. I'm looking forward to your workshop. Okay, so sort of the seminal implementation of this was Sage in 2008. This is a white box fuzzer that has been used internally at Microsoft to basically test all of their Office products and all of their operating systems from Windows 7. And so they recently decided, hey, maybe everybody needs this technology, and everybody does. So they released this as Project Springfield just a couple weeks ago as this Microsoft Security Risk Detection package. So you can actually do this for your Microsoft projects. The stuff that we're doing is all Linux-based, so we would use AFL Fuzz, or libfuzzer is Google's implementation of a smart fuzzer. So both of those would be what you would do if you were running it on Linux. Okay, so is it better than Santa Claus? So this is Linus Torvalds just a couple days ago, and he thinks that this is awesome because it finds all these latent vulnerabilities, and we know he's not keen on Santa Claus, so to him, it's better than Santa Claus, this fuzzing. Okay, so understanding fuzzing, well, I guess I'm interested in fuzzing, so we'll see that next workshop. So what is symbolic execution? Some people say it's algebra meets programs. For those of us who play CTS, this is CTS for the lazy. Because when symbolic execution started getting good, all of these CTFs got really easy for people to be able to score on. And I think there are several one-man teams that were using this to basically own all the binaries in the CTF. And I think Topher was thinking of trying to put some symbolic execution stuff in his CTF for BSides. I would imagine if there are any binary analysis programs in his CTF, you could use this stuff, the software you have right now, to get those flags without actually having to do the work of reverse engineering the level. But I don't know yet. We'll see. So CTFs. So we're in a security workshop, so I'm assuming everyone has at least known about CTFs. So the idea here is to figure out some magic input that will get you a flag. And so for the CTF that I run in the malware class and the CS201 class, we have figure out a password to get this binary to print good job. That's the format of all of our CTF levels. And then we do all sorts of weird things to make it hard to find out what that password is. And this is all, the format of every single binary in the CTF is the same. You've got a binary, figure out how do you get it to print good job. Okay, so I'm gonna write the code in Python. All of our code is in C, but it's easier to look at in Python. So here is an equivalent of this program in Python. You take some user input, you see if it's equal to some password, say it's Hunter2, you print good job if it is, otherwise you print try again, okay? So as a simple capture the flag level, there are so many different ways you can solve this level. You could use object dump or readelf to dump the binary and see all the strings that are in it, to see, oh, there's a string Hunter2, let me try that. You could use ltrace to find the comparison. So ltrace hijacks the library call strcmp, and you can see the comparison of whatever you typed in with Hunter2 going across the library call, and you can figure out the password there. You can use a debugger, and then just set a breakpoint in the strcmp, or wherever this conditional jump is after the strcmp, and just inspect the memory directly. So easy level, multiple ways of doing this. But here's a more complex capture the flag level. This is something that you would see in a sort of an intermediate level in a CTF. So here is a complex guessing game. You have some kind of encrypt function that just takes a string and modifies it in some random way, deterministic but random way. And then you ask the user for the input. User input is that. And then you encrypt the user input using some amount 1, and you see if it's equal to the same encrypt of Hunter2 with a different amount, like a different key. So as you can see, that's a little bit harder, right? Because now there aren't many solutions to this, right? So you can't use object dump or readelf because Hunter2 is there, but it's not the password anymore. It's not what you type in because these two things are encrypted differently, right? So now you can't do that. You can't use ltrace to find the comparison because now the ltrace is comparing the encrypted results. All right, so that doesn't work. You can't use a debugger for the exact same reason. Your option is to reverse engineer the encrypt function and then figure out, which is a pain. Like you don't want to be doing this in the middle of a CTF. It's sort of it's difficult, and it's it's not good pedagogy, right? Like you reverse engineer someone's random encrypt function. How does that really help you learn anything new? So that's sort of unnecessary. So the solution, and the solution I'm going to teach you to solve this automatically, is symbolic execution. And so what is it? It's a system that allows you to walk through all the possible paths of a program. Well, all mean within the limits of the amount of resources you have on your computer. So all is an asterisk. And so I'm going to work through an example here. So you're here, and the goal is to get to this part of the code. So you're interested in reaching a good job, and you would like to tell the symbolic execution engine, what is the input that gets me to line 3? And that's the abstraction of symbolic execution. And that's why you're like, hey, I need to get this line of code executed. Let me work backwards, and you give me the input for that. Okay? So for symbolic execution, the first thing we do is we inject a symbol. And in this case, we're going to inject the symbol on user input. But first, what is a symbol? Do you remember high school algebra? So I don't remember much math beyond high school algebra, so this is really fortunate. So if they have another one that relies on calculus, I'm going to be in trouble. I'll have to relearn calculus. But algebra, I know algebra, and this is basically what it is. So think of a symbol as that variable x, but instead of it being in an equation, it's a variable in your program. You don't know what x is. You want to find that out, and it's the same as a symbol. So x depends on the equations that constrain it. We're going to talk about symbols as depending on the execution paths that constrain it. Because based on a certain value of that user input, it's going to traverse different parts of your code. And you need to know which constraints are on that user input to get to different parts of that program. Okay, so let's talk about an execution path. So an execution path is a way to travel through a program. So for example, you have this program again, and you have 2 possible execution paths through hunter2, through user input is equal to hunter2 and user input not equal to hunter2. So the first thing we do is we talk about how execution paths constrain symbols. So here we set the user input to a symbol, and then as we evaluate different parts of code, we will sort of we will calculate a symbolic value for the user input, and then execute based on these symbols. And so for this particular path to be executed, at the end, at this line, you can see that the symbol has this constraint that it has to be equal to hunter2. Now this is a really trivial example, but you can think of, you'll have multiple kinds of constraints throughout your program to satisfy. So how does this work in a symbolic execution engine? So the first thing you do is you inject that symbol. You say, instead of user input, I'm going to inject lambda, which is my symbol for user input. I am going to branch if there is a condition. So here is the first part of my program that relies on user input as a symbol. And so here you branch. And so what does it mean to branch? Well, it means to split your execution state into 2 different possible paths. And then what you do is for each of the paths, you update the constraints on your symbol based on that path you're executing. Okay? So here on the left, you have executed that path where lambda has to equal hunter2, and then here it doesn't equal hunter2. So those are your constraints. And then what you do is you evaluate each branch with your symbols. If you evaluate the lambda does not equal to hunter2 branch over here on the right, and it turns out you terminate the program before you get what you're looking for, which is a print good job, you can immediately get rid of that state, no longer needed to explore, and then you continue with the other branch. And then when you continue with the other branch, you'll see, hey, I'm actually on this 3rd line that I had intended. That's when I ask the symbolic execution engine to say, hey, what are the symbols that meet the constraints on that path? And then it'll give you the result. And if there is a variable that satisfies it, it'll give you the symbol value, the concrete value of the symbol. If it's unsatisfiable, well, in this case it is satisfiable, but there is a case where it's not satisfiable, it'll tell you that. Okay. So here is a more complex example, and this is so some people here have taken my CS201 class. This is a simple level that I give my class that has them go through a set of conditionals to find out what the input is that will print good job. So if this function returns 1, it'll print good job. Otherwise, it'll print try again. And so the idea here is, I just want to show this to you. It's just a sequence of branches that will always return 0 if any of these things hit. And as it turns out, there's one number. So this secret is not given to them. So I give them a binary. So I compile this into a binary. I give it to them and say, what's the integer that gets this thing to return 1? And so I'm using this example as a way to show you what happens in the symbolic execution engine when it tries to execute this. So what are the possible paths? So here is a tree of the paths that this function can take. And so if you start at the top, it has this branch, and then it can fork either to return 0 or continue to the next one, all the way down. It cascades all the way down to the bottom right. And this is the thing that's going to get executed by the symbolic execution engine. Okay. So the first thing to note about symbolic execution is that there are many ways to execute this code. It turns out the way it executes it is to do a breadth-first search. Starting from the top of this tree, it's going to execute these things level by level. Okay? So that's Anger's default. The reason why you wouldn't do depth-first search is that if somebody puts a booby trap, like an infinite loop somewhere in the beginning, you don't want to be evaluating that infinite loop, right? So this is the reason why they take a breadth-first search algorithm on the symbolic execution. So this is basically, if you get all the way down to the path that you were looking for to return 1, you're going to have a bunch of constraints. So you remember, every time you hit this branch, you add a constraint to the symbol. So at the very end, that symbol that we use for input has all of these constraints. And with a symbolic execution engine, these are constraints that can be solved with this SMT solver. And that means a satisfiability modulo theories. So you have a bunch of theories here, and then you figure out what the input is that satisfies them, based on the code that you see. Okay. So here is the real world. Again, you have different user inputs, and you have your code, which is acting on these user inputs, and you want to figure out what is the set of user inputs that will generate this good job thing to be printed. So that's the magic. One of the biggest problems with symbolic execution is that these binaries can be complex. You're going to have a whole bunch of symbols, you're going to have a whole bunch of branches, and this thing grows exponentially. Right? And one of the beauties of what the Shellfish team did was to automatically identify which branches they should just ignore. Because you can't search 10 to the 65,000 combinations. You have to intelligently say, those things I'm not going to look at. I'm going to say, ignore that. And that's what Anger, the API for Anger allows you to do that kind of stuff. Okay, so how do we do this? So the UCSB folks, not only did they build this powerful tool, they actually released it for everyone to use. And so this is why we're using it. It's probably the most mature. We looked at, there's another one called Manticore that got released last summer, and I think Anger is probably the most mature of all the ones out there. So I think now you have enough that we can do some of the CTF levels. Do you have any questions? Yeah.
How does this compare to Sage, for example?
I don't know. Yeah, I'm not familiar. I know Sage was the gold standard for a long time. Sage does more smart fuzzing. I'm not quite sure how much symbolic execution it does, but I would imagine since Microsoft has been working on it for so long, I think it's probably the best that's out there. Any other questions before I continue to the scripts and programs? All right, so what is Anger? It's a symbolic execution engine. It allows you to step through binaries and follow any branch symbolically. It allows you to search for a program state that meets a specific criteria, and then it allows you to solve for these symbolic variables that you have going on through your program state, given either your path constraints or other constraints. Okay. Yeah, actually, we will need to specify the types of these things to give, when you define a symbol, you have to define the width of it. And then when you concretize it, you have to say, well, what kind of type is that? So we'll talk about that in the engine. So the foundation of symbolic execution is two things, execution paths and then these symbols. So we'll start with execution paths in Anger. So an execution path represents a possible execution of this program that begins somewhere and ends somewhere else. And the way it's instantiated in Anger is through this SymState object. And so, as the name suggests, this is the state of the program at any particular node. And this is a symbolic representation, right? Because you have injected some symbols and it has some constraints. So the SymState for any particular part of your execution path has where you at are in the execution of the program, as well as all of your symbolic state for all the registers, maybe all the files. If the symbolic values have propagated through your program, it's all the different places that could be symbolic, as well as the concrete state of execution. Okay, so a single execution path isn't really interesting to us. What we want to do is we want to see all the execution paths and then search them for a state that matches a particular predicate. For example, the state outputting a specific string, like good job, or a variable being a certain value. So those are the kinds of things that we're interested in, but we want to be able to have a set of execution paths so that we can search them. So how does Anger do this? How does Anger build a set of execution paths and then brute force search them? That's what we're going to talk about next. And this is a simulation of the simulation manager in Anger. And again, we'll use this same function. So Anger stores and handles the set of all possible paths in your program in a thing that they call the simulation manager. And then this thing was going to allow you to step through the program to generate your paths and states. So here's the algorithm for doing so. It starts the program at wherever you tell it to. So you can start it at the beginning, at main, or you can start it in the middle of your program, and then if you have some memory locations you want to be symbolic, you can initialize those there. So you don't have to start at main every single time. Especially if some CTF writer has put a booby trap for Anger right at the beginning. You can start the program right after the booby trap and then make the output of that booby trap sort of a symbol that you can use later on. And this will become clearer later. And then what you do, the algorithm is to execute every single instruction in a state until, every single instruction in an active state until you reach a branch point. And so if you reach a branch point, this is where you have to split that state into two. So going into the branch point, you have one active state. If you hit that branch, now you'll have two active states. And so you'll create another state in that in the simulation manager, and you'll have a second state. The other thing that happens is that if the state terminates, you just get rid of it in your set of paths. And then, so at every branching point, you're splitting the state into multiple states, and you're adding them into the set of active states. So you repeat until you either find the condition that you want in that program, or everything terminates. And if everything terminates without you finding it, then it says unsatisfiable. Can't get a condition that meets that location. Okay. So here is an animation of what's going on. So at the first thing, say this is the first part of your code. The initial state is in green. And so I am here at the green one, and I execute this, and it's a branch. So then I create two active states from that, and then the blue is already executed. So this ends up going out of the simulation manager. So now you have two active states in this simulation. And then you execute we're doing breadth first search. So we'll execute this one on the left. It's a return 0, and a return 0 will eventually terminate. So the simulation manager will terminate this, and it will execute this statement. And from here, this will generate two new active states, and so on. And you go all the way down the tree doing this until finally you're here. And now every time you've done the branch, you've updated the constraints on that branch. So at the very end, you have a return 1 condition, and this was the point in your code that you were interested in. This is the one that you told Anger, hey, I'm interested in states that execute this line of code. And by getting all the way down here, you're basically brute forcing execution symbolically. You get down here and say, hey, Eureka, I found it. You have a set of constraints that have accumulated from the top of that tree. Now you can say, Anger, or SMT solver, solve these constraints. So that's basically what's going on inside the engine. So what do you search for? So we're going to search for a lot of different things. One thing on the left is, hey, you see this backdoor at PLT? I want to figure out the input that gets me that backdoor, but I don't want to reverse engineer someone else's stuff. So that's what you can do. You say, hey, anytime if you find a state that actually reaches this address, that's what I'm looking for. What was the input that generated that? And then the constraints will be applied, and Anger will tell you, hey, this is the string to launch that backdoor. So that's one way. If you have a piece of malware, it probably won't be named backdoor. It might be named some Windows thing, like what would you look for? Create thread or unmap memory or something like that. That would be what you would be, hey, this piece of malware, what gets it to unmap all of memory and load something else? Okay. Or in our case, what if maybe we would just want to check a variable to see if success is equal to true, or maybe we want to check standard out. If standard out has good job in it, that's my state. So that's like all of my CTF levels. You could do that. So that's basically searching for what you want. And so both of these approaches are trivial in a symbolic execution engine. Basically, at each step of that execution, you just check those predicates. The predicates that you're interested in, you just check them. Every state that you generate, see if you meet it. Otherwise, keep executing. Keep blowing up that tree until you find something that works. Okay? And we can define arbitrary functions for this, like for searching for what we want to look for. Okay, so this is the biggest problem with symbolic execution. It's the state space explosion, right? Every if statement splits it. So it doubles the state every time you branch. And so there's no known good solution to this problem. So here's an example of a program, and you basically have to search all of this stuff and keep on going. So that's no good. One of the things you can do is to avoid certain states. And this is what the crackadder, this is what they must have done with crackadder when they automatically exploited it. So here is your tree. If you can figure out that following a certain branch will lead you to a part of the program that is uninteresting, then you can tell Anger, just prune that. I'm not interested in that stuff. Okay? And this allows you to cross off, like if you said this if statement, if it goes there, just cross off the entire thing. That allows you to basically terminate like half of the state graph there, right? And this is basically what smart fuzzing kind of does. Smart fuzzing is like, hey, you know what? I'm going to concretize this if statement to always go that way. And then you can then execute that side of the thing symbolically. So that's smart fuzzing with symbolic execution. That's why they're combined in the CGC implementation. That's the power of it. Okay, so on the left, there's a variable here that's set that's not going to find us anything useful, so we cross that off. And then we only analyze the right side, and that saves us a lot of time. And it turns out maybe the successful state is down there, and I don't have to search the left half. So that's the goal. Okay, so avoiding paths. So if we know we can avoid states in the exact same way we can accept them as successful, that will really help us, right? So here's my success state. Here are all the states that you can just ignore. Just stop, don't branch. Don't create new states off of these other conditions. Okay, so how do you figure that out? So this has to be done with human intuition. I mean, you can get some computer heuristics to work to figure out, oh, this set of code is not interesting, it won't lead you to anything new. And that's what Driller does. You can do that automatically. But for mere mortals like me, you would analyze the program and say, hey, maybe I don't care if the input's over on this side, and I'll just look for more interesting input. I am not, in this talk, going to have enough time to talk about Vera testing. This is the CMU way of figuring out how to prune states automatically that aren't interesting. And that's sort of like the heart of good smart fuzzing algorithms. Okay, so what you would like the algorithm to do for finding certain states and avoiding certain others is, so this is basically a modification to that building the set of paths. You want to load the binary, specify a starting point to create that simulation manager, and then run this loop. Step all the active states, and then branch if necessary, and then run your predicate. If it's a should accept state, then you have found what you're looking for. You can exit the loop, return to the user, and say, found it. If you are if the should avoid state triggers, then you know you can just terminate that thing immediately. I am not going to search on that state anymore. Wherever it goes in the program, I don't care. Just tell the simulation manager to stop right there. And that's this will prune the states that you're not looking for. The other thing that you need to do is that any state that has terminated, like called exit, you can get rid of. So that's the algorithm, and that's what Anger is doing in an infinite loop, basically, until it either finds what you're looking for or terminates and says unsatisfiable. Or it sits there in an infinite loop, or not an infinite loop. It sits there executing that program forever, and then you have to determine the halting problem on it. So for all the CTF, the CTF binaries I have given you, Anger will solve all of those within a minute. So if the thing is running more than a minute, then your script is probably got an error in it. So just wanted to let you guys know that. Okay, so Anger saw that this particular paradigm of encoding accept states and encoding avoid states was used everywhere. So Python, Anger is written in Python. It's got the Python binding. So what they have implemented is in your simulation manager, there's an explore method that allows you to say, find this path and avoid this path. And these are predicates, like we had talked about earlier. They're predicates on your execution, some state in your execution. The other thing that this will accept is addresses. So say you want to find the input that hits this address while avoiding all inputs that hit this address in execution. You can specify that with Anger as well. Okay? So search for this address and terminate on this one. So that basically is the explore method, and this is the method that we're going to be using quite a bit. Any path that is accepted to the list simulation.found will, so if you see this predicate and it triggers, you'll add it to simulation.found, or all the acceptable states are put into this part of the simulation manager. And if you have a state in the simulation.found, you can then take the symbols that are associated with this program state and concretize them to figure out the actual input there. So this is a bunch of constraints. That state has a bunch of constraints, and then you can actually ask the SMT solver to solve them after the execution is done. Okay, so now we finally can get to the angry CTF levels, and we'll start with the hello world of Anger. This is our hello world of Anger, and if you look at this is a simple buffer comparison. So this is basically one of the password levels. Enter in your password. There's no overflow here. Well, the overflow is the last level that we'll talk about. So here is buffer 9. You read in the password. It does an 8-character read. And then what you do is you send this to a complex function. And it's a function that's hard for humans to reverse engineer, but easy for Anger to eventually get through. We wanted Anger to take about a minute. Because we didn't want it so trivial that you could brute force. But this is something that it's complicated enough that people aren't going to want to reverse engineer this thing. And then what we do is we take so it basically will modify the user input and then compare it to some static string in the binary. Okay, and you see, as before, you're like, okay, yeah, I can't use my usual techniques to solve this. I need to use symbolic execution. Okay, so 00 anger find is the name of the binary. So if you unzip that file, and does anyone need the files? I have it on this SD card. And it's also at a URL. So in a debugger or disassembler, you can disassemble that function and figure out, hey, this is 0x804867A. This is the good job path. This is what I'm looking for, right? So I want to say simulation.explore and then find is equal to that. This is all I want to give to Anger and say, Anger, find me that password. And this is the abstraction it's giving me. So a little bit about the CTF. For every single level in the CTF, there is a template solution script that is mostly filled out except for a bunch of question marks or exclamation points. And these are places where I'm asking you to fill in the what's there. And this is sort of an easier way of learning Anger because you're not focused on all the scaffolding junk that's in there. You can just focus on the things that really matter. And so the easiest thing is, hey, I'm going to give you this script. And I'll step through here. This is the binary that you want Anger to analyze. And the imports aren't there, but we'll see. If you edit the scaffold 00, this is basically the same with the comments eliminated. So I'm adding the comments back here. So specify the binary. Then you tell Anger to create a new project, a simulation project with that binary. You instantiate the simulation manager based on this project. So the project will, you create this binary, this project with the binary, you set the initial state of the program to project.factory.entry state. So this actually is a special thing in Anger that says start at main. There's a different API call if you want to start somewhere in the middle of the program, and that's why this is the entry state specify starting at main. And then you want to create your simulation manager by setting the initial state, by passing it the initial state. So here is the explore command, and the explore command is going to just take the print good address, which we already found in the previous. And then what we're going to do is we're going to explore all the states here, and then when this thing returns, if the simulation has been found, and so this simulation will terminate whenever the find is hit. And then after this thing finishes, we're going to go and see if there's anything in simulation.found that hits this address. And then we're going to dump out the standard input that led to that address being hit. So we're going to ask the simulation state to dump what was that standard input. And so what this is this standard input was symbolic in the simulation state. And then when we do this dump, it will try and concretize it. Because there's actually multiple, there might be multiple inputs that can generate the string that you're looking for. And so if you are interested in more than one, there's a way of concretizing and getting all the different sort of inputs that meet this criteria. So let me show you that it works. So here's my virtual machine. So this is the state. That was the address that we said we were trying to find. And then reader. And then it will symbolically execute this thing. And it'll give you a password. And one of the things you can do, so if I run this, then qtemp xtyu, and it says good job. Right? Just from this script. Now, I didn't have to, aside from finding the state in that program I was looking for, I didn't have to do anything, right? And if I did a strings on this, so we were looking for qtemp, it's not there, right? It doesn't show up anywhere in your program. So basically what Anger has done is it brute forced that complex function and then figured out the thing that would get you this good job result. So that's the first one. Any questions? Go to the next level. Are you guys able to run it? Did it run, or is anyone running it? Or should I just? Oh, let me radar. So yeah, let me radar. You see, it's checking a different string, QWSY, and then it's down here. So So you see this good job is at 804.867A. This is Radar 2, the latest Radar 2, and this is the visual mode of Radar 2. Yeah. So, thanks to you, I know how to use it. He wrote me some levels in my class the last time that got me on Radar. And all the commands that I know in Radar are from his level. I don't know much. Yeah, you asked me just the bare minimum, and I can answer the bare minimum. This is the latest Radar. They've done the ASCII art rather than putting it in your browser.
Okay. Yeah,
So yeah, and in fact, my Anger instructions have instructions that do the browser, the web browser thing. So that doesn't. Yeah, I'm gonna get rid of that because this is way better for me. And it's got the Vim. It's got the Vim bindings to navigate the tree. So. Yeah, this is beautiful. Yeah. Yeah, I just wish I knew more Radar commands. Do you still need this address, or can I? This assumes you've installed Anger as well. Do you have Anger on there? Okay. Well, let me do the next level. The next level is as easy. Oh no. Okay, here's another level. So in that very first Hello World level, we were looking for a specific address to hit. We can do arbitrary predicates, right? We don't have to specify an address. We could say, hey, check for states that return certain outputs, like good job, right? So in this case, we're going to use Anger's find and avoid thing that I talked about earlier with the explore method. So the initial stuff is all the same. Create the Anger binary, or create the Anger project based on the binary, set the initial state to start at main, create the simulation manager. And then what we're going to do is we're going to say, hey, we're going to define two states. One is going to be the find state that's successful, and the other one's going to tell us to abort, like to terminate execution, to no longer continue. And then what we're going to do, and so these things are not specified, but what we're going to do is we're going to do a simulation.explore, and we're going to say find this state here, avoid this state here, and then you'll be able to automatically generate the inputs that lead to very specific outputs. And so one of the outputs that determines that you're successful is good job, right? If good job is in the standard output, then you should return true, which is basically what this level is asking you to do. If try again is in the output, then you should terminate. And so for this particular level, we force you to do this abort because after the try again, we stick you into an infinite loop, like good malware would do. If it thinks that it's running in a debugger, oh yeah, I'll just send whoever's trying to reverse engineer me, I'll send that person into an infinite loop. So you want to be able to specify, okay, if it's that state, just continue on automatically, or terminate that thing automatically. And then what I'm going to do is, if I found the thing in the simulation, I get the solution state, and then I concretize the input that led to that find state. And it's very similar to the very first level, except instead of your constraint being an address that you're executing, it's the output of standard out. And so this is just to get you the idea that the constraint that you put on to finding the state that you want can be any number of things. It could be a register, it could be the standard out, it could be the execution IP, the IP, the instruction pointer address, it could be any of those things. Okay. So define a function that represents the state you want to look for, dump standard out to a variable, and then test it. And this is being done symbolically. If the expression has good job, return true. And then this is same as is successful, but specify the state that should abort immediately. And then this is the explore method that takes those two things as named parameters, and that's it. So let's execute this. So here is my script, and it's exactly as I showed you before. It should just take a minute. This is a laptop, so maybe it's a little slower than what you would run on a desktop. And then that's your password. All right. Any questions before we get to the next part? So if I hustle, I can get you all the way to an automatic exploit. So I'm going to continue. Okay, so now I'm going to introduce symbols and constraints, because one of the things you might notice is that there were no symbols in the previous example that I had to define, right? I wasn't injecting a symbol anywhere. And as it turns out, Anger will inject symbols for you on certain inputs. It'll do that automatically. So in some cases, Anger will automatically inject a symbol when the user input is taken from standard in. All right? So that is why we didn't have to actually say, hey, here's standard in, make that a symbol. Typically, if you want a specific part of the program to be symbolic, you actually have to define, it's like declaring a variable. You have to declare to the simulation manager that all of a sudden this memory location and that register, treat those as symbolic. And so Anger can also handle very simple calls to scanf without complex format strings. You will need to inject symbols manually if the input is more complex. So Anger, when it hits scanf, a formatted scanf, there's a ton of branches. I mean, scanf is like, the formatted input is like basically like a parser. And if you send a symbolic execution engine at a parser, it's going to hate life. So this is why Anger won't execute arbitrary scanfs, and you have to do something else. And then if you substitute out that scanf, well then you have to inject the input from scanf that would have happened manually into your program. And this is what we're going to do to inject symbols into it. We're going to start the program somewhere other than main. We're going to start it like after the scanf, and then we're going to inject symbols for what we think scanf should have put in there, and then do the symbolic. So that's the next step. So you need to inject symbols manually if this input is more complex. So arbitrary format string for scanf, you're going to have to do something else other than than what the first two scripts did. If you get input from a file, you have to define that file symbolically so that then Anger can actually use the data from there. If it's from a network, you're going to have to manually define where that network input goes into your program and define that stuff symbolically. Any interactions with the UI, you're going to have to do that symbolically. Okay, so how do we inject symbols into our simulation manager? It's done with bit vectors. So that's what Anger's symbols are represented by. Bit vectors have a size, the number of bits they represent, just like a type. And then with all of the data in programming, bit vectors can represent any type that can fit it. But most commonly, they're either integers or strings in Anger. And then the typical difference between a bit vector and a variable is that the variable stores a single value, a concrete value. But bit vectors, which are symbols, can store every value, right? It's just an abstraction for the actual data that's there. And within the simulation manager, you can either have a concrete value or a symbol, and the simulation manager will run the same way. Okay? And these the bit vectors store all the values that meet the execution path's constraints at that particular time. So, for example, you could have defined a bit vector, have it run through your program, and then in a particular state, your bit vector lambda, say it's 8 bits and and it runs through your program. At a specific point in that program, it might have these constraints. So it might have hit some branches, and gotten to a place where these are the constraints that should apply to this lambda. And that's the way the bit vector is stored. And then when you actually want to concretize that thing, you say, hey, you know what, I just want any value that satisfies these constraints. Then that's known as concretizing the bit vector, which is what we were doing after we found a simulation state that met our constraints. You concretize that for me. I want a specific input now that'll give me what I want. So that's concretization. And the thing that it gives back to you is a heuristic. Because there are so many different, so in this case, you'll see that the integers 2, 4, or 1 will satisfy this. It'll have to just choose one for you. You can tell it the kinds of things that you want it to choose, but it's basically done by a heuristic. One of the things about concretization is that there are certain symbols that you want to automatically concretize, and that's what smart fuzzing does. So it finds a symbol that it's like, hey, you know, that actually isn't going to affect too much of anything. I'm going to concretize that in my simulation so that I don't have to keep that state around, that branching state. Okay, so bit vector types. A concrete bit vector is basically the same as a variable. It can hold exactly one variable or value, so we call it concrete. So lambda is equal to 1, that would be a concrete bit vector, and then when you did the concretization, it would always give you 1. A symbolic bit vector is one that can take on more than one value. For example, if it's lambda greater than 10, and then you ask to concretize it, it's going to have to give you a heuristic of what it will return. An unsatisfiable bit vector is one that can't take on any values. So there won't be anything in that simulation.found that will meet the constraints, and then you'll get nothing. So here's an example. If lambda is equal to 10 while lambda is not equal to 10, that's unsatisfiable. So if you get to that point and you say concretize lambda, it'll say unsatisfiable. And then the last one is unconstrained. This is a bit vector that can take on any value. And the reason why this one's important is because when you do a buffer overflow and you have some memory location, like a return address, as soon as you find that a return address is unconstrained, that gives you an exploit, right? So that would be the condition that you would check for on a sort of an automatic exploit program to say, okay, I found something that I can own. So these are the states. Yeah. Yes. So you can actually add constraints. So if you have, hey, this thing is, this is symbolic. So technically you're asking from if I have a symbol that could be any number of values, but say I want to add another constraint that says the top 16 bits are all 0, you can add that as well and then say concretize that. Okay. I don't know Anger well enough, but yeah, you can. It will give you a value. It will give you any value that matches the constraints, and it's done by a heuristic. Yeah, there are actually there's some very crude things, like you can do a minimum. Give me the minimum value that satisfies the constraints, or the maximum value. I think that's in the next slide. So yeah, so solving constraints actually. So Anger is actually a front end to Z3, and Z3 is the constraint solver that Microsoft developed as part of Sage, and then they open sourced it. And so Anger is basically using the same technology that was running the Sage. So you can find any single value, and I believe that's Anger's choice, which single value gives you. You can say up to n possible values. So, and again, I think the n possible values are Anger's choice. Although I'm guessing. This is a total guess on my part. The maximum or minimum, or to just ask if this bit vector is satisfiable. So I don't know enough of the interface to be able to say. I would imagine there's probably better heuristics or better ways of specifying. But definitely, if you have specific constraints that you want to add, say I'm only interested in the values that have the last bit cleared, you can actually add that as a constraint. And actually, when we talk about this automatic exploit, we're going to actually have to constrain our return value to point to a specific address, that's a constraint that we will put onto anger, and then it'll find us the input that matches that. Okay, so symbols in the context of program state. So again, we're going to inject symbols in order to specify the particular values. And then as the symbol goes through this program, it's going to collect constraints. As I mentioned earlier, we can manually add constraints of our own if we wish. In terms of executing this symbolic engine, one of the things we have to talk about is symbol propagation. So whenever you have operations on symbols and the results are stored elsewhere, those symbols will propagate to whatever destination they've affected. So here's a case where user input is lambda, and then it's used to generate encrypted input 0, and then encrypted input 0 goes to encrypted input 1 and propagates. Well, anger has to keep track of all of those symbols. So it has to figure out the locations of each one of these values and then propagate the constraints and the symbol over to those locations. And it's doing this automatically. So on the right, you see the memory, and you see that user input is green, which it says it's symbolic. And then eventually, as you execute this program, the encrypted input 0, 1, and 2 are also marked as symbolic. And this is how it keeps track of which states need to be evaluated with constraints. So in this case, the variables encrypted input x depend entirely on user input, and so that's why the constraints are propagating up to it. So here's an example of forward propagation. Say all of a sudden the user or someone decides that lambda is going to be 10. And I say, I'm interested in all things where lambda is 10. Then basically what this will do is it'll concretize user input and then propagate that constraint all the way forward, or propagate it through all the constraints forward, and then you can solve for encrypted input 2. It's just algebra. So this is why it's algebra for your programs. The more common thing is to do the opposite, to do reverse propagation. So if you add constraints to the symbol values that have been propagated and ask it to solve backwards, that's basically what we had in that first level, right? We found that, hey, we're in good job. We want to figure out what that input was. And so this is constraint reverse propagation. And so here we say, hey, the encrypted input is 14. What was lambda? And this is more typical of what happens. 14 will say, oh, encrypted input 1 is going to be 2, and then encrypted input 0 is negative 13, and you get lambda is negative 10. And this is how, when we had that encrypt function and it generated this intermediate string, this is how we solved backwards through the complex function to find out what the input was that went through the complex function to generate the string that matched. This is basically reverse propagation of the constraints. Okay, so the NP completeness of constraint satisfaction and the inevitable heat death of the universe. So it turns out not only is state explosion a huge problem with this symbolic execution, but it relies on solving these pretty complex systems of constraints. And so this is an NP complete problem. And so the theory term for no bueno. So we have to figure out a better way of addressing this. So that is injecting symbols. One of the other things we can do to simplify the constraint problem is to apply constraints of our own that will limit what we're looking for. And I'm going to give you examples of 2 common patterns. The other 2 patterns, they'll be in my slides. I'll put a PDF somewhere in my up on my course page. The 2 I'm going to do are registers and global memory. There's ways you can inject symbols into the stack and on the heap. So those are the stack, the heap, and then from a file. Those are other examples in the CTF. So we're just going to do registers and global memory. So here's the examples. You have some user input, and say this is a complex user input. So Anger is going to, if it's a simple user input from standard in, Anger handles that easily. But say you have this crazy formatted input, and it does all sorts of branching and loops and these sorts of things. Then what you want to do is, hey, when this user input is finished, if this program, the input part, initializes 3 registers with the result of that user input, then what I want to do is say, you know what, I'm not interested in parsing this and executing that symbolically. What I want to do is just turn the results in these registers into symbols after the user input has executed. So I'll execute the user input concretely in Anger, and then say stop after this user input, and then I'm going to inject my symbols into these registers, and then I'm going to symbolically execute forward from there. So that's basically what we're going to do when we inject symbolic registers, initialize these registers. We're going to go to the part of the code where these registers have been initialized by the get input call. We're going to turn those into symbols. We're going to send them through. We're going to create our initial state of the simulation manager right there. We're going to send those through. The output is going to be symbolic. We're going to, again, apply this reverse propagation, apply the constraints to figure out what those registers values are. And then we're going to concretize those registers to get the actual input that would come out of this user input field. Okay, so here's an example. You have this get user input, and it does all kinds of crazy looping and format parsing. And you reverse engineer it, and you see that, hey, at the end of this get user input, there's 3 register moves, and this is source destination, where the registers are saved off into the stack somewhere, and then you execute the rest of the program. And so the way to do this in Anger is to specify in your simulation state. So you have your simulation manager, and then in the simulation manager, you have a bunch of states that represent paths. For a specific state, you could say, hey, I want the register EAX to be equal to some symbolic bit vector that I define. And that's what I'm going to do. That's how I'm going to initialize a symbol into this register. And this creates a symbolic value into that register for that simulation state. Another example is global memory. Say your user input function ends up writing its output into 3 different locations in read-write memory, in global memory. And you don't want to have the symbolic execution engine execute the user input, so you cross that off. You start the program right after user input, and you manually inject symbols into the memory that it would have initialized. And then you tell the Anger to start there and then execute forward to give you your output. Okay, so here's an example of this. Say you have a scanf %u%u, and it goes into these 2 memory locations. So these are 2 unsigned integers. And you see in the assembly, it does a push for these 2 pointers, 128 and 120, and then it calls scanf, and then this is the format string. So those are the 2 addresses that after this call to scanf, you're going to turn into symbols. And then you're going to ask Anger to start from after this scanf and then execute forward using those symbols. And then when you're done, you can say, hey, I'm going to concretize those into integers because I know that they were read in as %use. And then I don't have to worry about the fact that Anger doesn't like formatted scanfs with multiple fields in it. And then you win. The API for doing this is similar to the previous one. You say state.memory and then store at this address my bit vector. And that instantiates a symbol for that address in memory. Okay, so we're going to do 2 levels that do exactly these 2 things. Symbolic registers, symbolic memory. Symbolic registers. So here is if you reverse engineer, if you put this in radar, you see this get user input, and you see this EAX is being moved into memory, EVX is being moved into memory, and EDX. And so this is basically the output. So what get user input does is it initializes these 3 registers and then it returns. And then from there on, the program is using those as sort of the password. Okay? Right. And this is the reverse direction as the other one, so that's why I put that there. Because I get the direction confused all the time. So here is the program for solving this. One of the things is that where do you want to start? So, and here I give you the answer already, 88D1. If you look at this, you want to start right after the get user input has finished. So this is 88D1. This is where you want to inject the symbols because then the symbols will propagate into memory, and then the program uses those memory locations to figure out whether or not the password is what it is. So that's the beginning of it. And then what I'm going to say is rather than use the entry state, I'm going to say initial state is this blank state that starts at this address, the address that I specified. And then anger is going to start in the middle of your program. So it doesn't emulate that scanf call that it doesn't like. And then what I'm going to do in anger, there's this clarity package, and that is the package that is used to represent symbolic values. That's the thing that implements bit vectors. So in clarity, to specify a bit vector is this .bvs, clarity.bvs, and you give it a name. How do you want to name that symbol? And then the number of bits in it. So in this case, we know that these, because it's %use, well, we know it's %use, you can figure out that these are all %use. So you say 32 bits. They're 3 32-bit numbers as the password. And then they're labeled password 0, password 1, and password 2. And then what I'm going to do is I'm going to initialize the state. So you see I started the state at that virtual memory address. And then I know what the register values I want are. So EDX, EAX, EBX, and EDX. And I set those to each one of these symbols. So now you've instantiated the symbols into your program. And then I can create the new simulation manager, which is this line. And then I say, hey, find is successful and avoid should abort. And the rest of the level is the same as the previous level I showed you. So just assume all that stuff is the same. And then if you find something, then because I have 3 different symbols, I need to concretize 3 different symbols that make this state satisfied. So that's what I'm doing here. And the way you concretize a symbol in anger is to use the eval. And by default, eval will assume that the thing you're giving it is an integer. If you wanted to evaluate it into a string, you can do something different, which I'll show later. Okay? I don't know, but I think because you have satisfied the constraints, because this simulation has been found, there must be at least one. Yeah. Okay, so this is, yeah.
The value right after EAX.
Yeah, there are a bunch of question marks in there because I want you to label it. Yeah. So with CTFs, it's hard to figure out how much to give and how much not to give. So it's like, yeah, you can figure out your own registers on there. I think there's enough here to get the flavor for it, and just to show you that it runs. So again, this is the exact same thing. And then, because I'm not in Python 3. So anger is Python 2. Sorry. Hey, I'm a beggars can't be chooser, so I'm like, yeah, I'll take the Python 2. So this is the password, and then and good job. All right, so we're good. How much time do I have? Oh, yeah. Okay, symbolic memory. So in this case, I'm going to do a scanf, but I'm going to read it into global variables. And so here's the scanf. It's pretty simple. It's a %8s, %8s, %8s. And this is being read into an array of 8-character memory locations in global memory. So you see the addresses here. This is hex A29FAA0. This is FAA8, AB0, AB8. So now you know that in order to get out of this scanf, you're going to have to put symbols at these 4 locations, because these are pointers to memory where the string will get sent into. Okay, so this is the program. Again, start address right after the scanf. I'm going to set the initial state to be at that address. I'm going to define 4 passwords, because there's 4 memory locations that are there. I'm going to set the password addresses, and the password addresses were exactly what I had just pointed out with the pushes before the scanf, those 4 addresses. And I'm going to create, I'm going to take that password, the symbol. So again, I declared these symbols, password 0 to password 3. I specify where I want to put them, and then I use initialstate.memory.store to store that password symbol into that address that I specified. So this is injecting all the symbols into global memory. And then I'm going to create the simulation manager. I'm going to do the exact same thing. Is successful or should abort. Exact same idea. And then I'm going to do an eval. And because these are strings, I don't want the integers to be passed back. I want the eval to treat those as a pointer to a string. And this is the syntactic sugar for saying, hey, cast this thing, this password 0, cast it into a string, and then output that. So that's the program there, and I should know to use my animation rather than just go straight through the program. It tells Clarity how large the values are, attach the symbolic values, check if solution found. Okay. So let's run that. So that's my address. These are the addresses of, or the address to start, the addresses of the password. I instantiate them. I say is successful or should abort, looking for those strings. And then I concretize all 4 strings, and then I'm done. And this should run. It runs longer because there's 4 inputs, and that's a lot of different, lots of computation going on there. Hope it doesn't overheat. All right, and then you can run this level. And find that is your string. Okay. Okay, part 3, handling non-trivial behavior. Give you a simple example. You can easily booby-trap symbolic execution. Here is an example that iterates through 16 elements, and each time it branches. So if you know Python, you can parse that and see what it's doing. So it's saying check all z, num z is 0, and then for I in range 0 to 16, check if user input I is equal to the capital Z, and then add 1 to num z, otherwise pass, and then return num z is equal to 16. So that's just checking to see if you have 16 z's, right? But if you look at all the branching that's going on here, Anger doesn't know that. Well, it actually does because it's smarter now, but it used to not know that, and it used to be a total haze, because this is actually, every branch splits your execution tree. This is 65,000 branches to Anger, right? So this is no good. Especially since this thing could be a single compare, right? A single strcomp. So the idea here is to automatically look at something like this and create a summary of that. That's much easier to execute. That's the name of the game that we're talking about here. And this is one branch, much better. So there are algorithms that will automatically deduce the insight on the previous slide. And this is where all the research in symbolic execution is going, is to try and do more stuff automatically. But nothing works as well as human intuition, if you have it. Sometimes I wonder if I do. So for complex functions, for complex functions that humans can easily reduce, so stuff like scanf, we can sort of understand what the scanf output should be, and not have to worry about running this parser through symbolic execution, then we would sort of inject our summary using symbols. We want the same thing to happen for these algorithms, but we want to be able to replace certain code with just its summary written in Python. There are 2 ways of doing this. One is to apply constraints, extra constraints, onto the symbolic execution engine. The other thing is to hook the problematic function and implement a Python routine that basically emulates it. And in that Python routine, it's done concretely, so you're not actually causing the symbolic engine any issues. So here is that check all z in code. So you have some string located at this address, and then it calls check all z, and then you know that if this thing checks out, you print good job. Well, one thing to do is to say, hey, at this location, you tell Anger, I am interested in any execution that gets to 77C. And then what I'm going to do is, because I know what this check all z does, I am going to add a constraint at 77C that says the characters at this address should be all z's, and if so, return. And then I completely avoid check all z, because I'm just checking the constraint before I execute that thing symbolically. You guys follow? Okay, so that's basically constraints. The other way to do this is with a hook. I'm going to re-implement check all z in Python and get something easier. There are two ways to do this, function hooks, and the way you should be doing it is with sim procedures. So function hooks is the low-level way of doing it, and then the Anger folks realized that this was happening all the time, so they created some syntactic sugar to make this a little bit easier to deal with, which is what a sim procedure is. So here is the way a hook works. So again, you have a certain amount of code in assembly that implements check all z. So here you're creating some stack space, you're pushing an address, you're calling the function, and then you're updating the stack to restore it. So what you want to do is you want to hook these 4 instructions with something else. And basically you're going to hook it with a Python function. So the idea of a hook is to say, hey, instead of this, instead of the 16 bytes that are here, I want you to hook this and execute a different piece of code instead. So here is the hook walkthrough. So again, these are the instructions you want to skip. You could imagine defining a function, a replacement check all z, that says, hey, you know what, at the end of this check all z, I want so you're looking for this to return 1, right? So it's going to check all the z's and return 1 if it's all z and 0 otherwise. You're going to say, I'm going to set EAX to be whether or not this destination is equal to that string in Python, and then I'm going to return based on that. And so that's my summary, implemented in Python concretely, and that's how I'm going to get around this thing. Yeah?
What are the problems if the variables aren't ever really out of, or aren't ever put in a line? Because we're assuming we're loading the
Then you would have to do it you'd have to make the register symbolic.
Okay.
Yeah. Yep. So this is the syntax, and you can just look at it and then ignore it because we're going to do something else. But this is how you specify the hook. I'm going to hook at this address, which is the beginning here, 16 bytes, and then I'm going to hook that with replacement check all z, and it's all going to work. Okay. So this is visually what's going on. This is the Python code you're executing. Instead of executing this symbolically, you're going to execute this concretely, and then continue. Well, not concretely. It's actually, if it gets a symbol, it'll execute it symbolically and return a symbol. But in this case, because the all z's was concrete, that's why I mentioned that. This is actually going to be a symbol that you're comparing to a concrete value. Okay, so hooks are useful if you want to inject symbolic values partway through execution, or replacing complex functions with simpler ones, or replacing unsupported instructions. So, for example, most system calls you don't want to follow through with the engine. Okay, so again, replacing complex functions is so common that they implemented some syntactic sugar to make it easier. And so this is called a sim procedure, and it provides a really easy way to replace a function with a summary. So if you recall x86 functions, push parameters onto the stack, and then you issue the call, which does the push return address onto the stack and the jump. Inside the function, you handle the parameters, you execute your function, you write the return value to the appropriate location, which is EAX. You pop the return address and jump to it, so that's the ret. And then eventually in the caller, you're going to pop the parameters. So what a sim procedure does is replace 4, 5, and 6. It assumes that it gets control of your program right after the jump to that function address. So this is where it hooks at the beginning of the function. And then this is all Python. including the return value. You can specify that in Python, and it'll map directly into the call stream of your binary. And then the rest of the binary is executed as x86. So here is the same thing, this replacement check all z, implemented as a sim procedure. You basically return whether or not this input, so again, it's handling all the input parameter stuff, so you give it the list of input parameters to this function, which is just one, it's the input, and then you just check to see if that input is the string of all z's, and then you can return off of that using Python's return, and then the piping will just work. Okay, so sim procedures are used to replace anything you don't fully understand or don't want to test for bugs, or that is unsupported by Anger. All right, you can write your own. Right now, what the Anger folks are doing is trying to re-implement a whole subset of libc with sim procedures to make those no longer stumbling blocks for symbolic execution. Because every time you hit a libc call, there's lots of branching in there, and then the engine's going to hate it. So, especially if it's not something that, if you're not using obscure conditions in there. Okay, I'm going to skip beta testing. That's the way of automatically doing that. So, the implementation in libc is important because a lot of these dynamic library calls are going to be automatically replaced. So Anger will automatically replace them with easier ones that it knows of. So there's an expanding library of them. One of the things is if you decide to statically compile your binary, Anger doesn't know what to do with that. So if you have a statically compiled binary with libc, you're going to actually have to say, hey, I am going to hook this scanf with Anger's scanf sim procedure. You have to do that manually. So that's what I'm in the level. So all of this shows up in the levels. So in the scaffolded levels, there's like 18 of them, but I'm only showing you like 6 of them. But the rest, everything that I show here has a level that shows you how to do it in the CTF. And so this is one of those. Okay, so this is the idea. If you see them in a statically linked binary, you just replace the sim procedure with a scanf or a rand or whatever you need, and then continue on. Okay, so let's get to the CTF levels. Anger constraints. So this is the first one. Let's see how much time I have. Anger constraints. So after this complex function is called, you have this check equals for AA, B, B, C, C, all the way to HH, where you're checking this encrypted input, 16 characters of it, and this does that check that has an inordinate number of branching. And what you want to do is basically, so all it's doing is checking against this reference password. So what you want to do is in this particular level, you want to add a constraint right after the complex function that says, is encrypted input equal to that string? So this is where Anger falls over. Anger will fall over if it actually executes this function, but because you know that this function is just doing a strcomp, you can just add that strcomp constraint directly. So that's what we're doing for this particular level. So this is basically where you figure out what scanf is doing. This is actually one of the hardest levels in the CTF, and it shows up in the middle, just because you need constraints to do the last part. So what you're going to have to do is you're going to have to skip scanf by making the buffer symbolic and then starting right after the scanf returns. And if you look at this scanf, the scanf has basically it's pushing a buffer onto the stack and then a 16-character buffer and then doing the scanf. And then here, it's after the complex function, it's doing this call to the check equals to that string. So I don't know how this happened, that it was like this, but. So the password is at 804A050. And then we want to constrain the symbolic buffer, because what happens is it gets past a complex function, and then it manipulates it. And then we want to put a constraint on that buffer, 804A050. We want to constrain that to be this string, which is the string it checks for. So we've conveniently named the function, so you don't have to go searching for it. That's the constraint. So this is the Anger program that does this. Again, we're going to put the start address right after the scanf. We're going to create that symbolic string, the 16 byte symbolic string. So this has to be, the bit vector size of that is 16 times 8. So because it's a 16 byte string, 16 times 8 bits per character. The password address, which we found earlier, that's where we're going to inject that symbol. And then we're going to store it, create the simulation manager, and then we're going to specify when we want to apply that constraint. So that is just before the check equals. So we'll see here we're going to put it right here before the check equals at 7.3. And then we're going to do a simulation explore, and we're going to actually say, find me states that actually hit that check constraint. We're going to find a whole bunch of them, right? And then we're going to add a constraint. So what we're going to do is, if the simulation has been found, then we want to check the constraint of the symbol that's in memory. And so what we have to do is we have to go into the simulation manager and the state in the simulation manager. We have to pull out the buffer symbolically. Because right now that buffer is a symbol. It's not actually a concrete value. You pull that symbol out of the simulation state, which is basically what this is. This is a solution state memory load. You specify the address of that string and the size of it, which is 120. I think this is actually bytes, so this would be 16 bytes. And then you say, hey, this constraint parameter desired value has to be that string that I implemented. And then you add the constraint onto the bit vector, and then you evaluate and figure out what's the input that generated that. Okay, I am going to skip the running of that, but trust me, that one runs and gets you what you need. The next level after that, or 2 levels after that, is what happens if you call this thing everywhere. So this is trolling the constraint checker. Say you're checking for whether or not it's equal to that string in a whole bunch of places, and that's what we do. Well, then what you have to do is you have to implement things as a sim procedure. Because so in this case, if you do a grep on this thing, if you get object dump this Anger sim procedures, and you check how many times this thing appears, it appears 256 times in your binary. So you could write a program that does that, in an Anger program that does that constraint checking 256 times. Or what you could do is just hook the sim procedure and then let it run to do that thing. Okay, so instead of hooking that function, or instead of using constraints on that, we're going to use a sim procedure. And the way we do this is to do it via a subclass of Anger sim procedure. And so here is a function that you might want to use a sim procedure to implement. This is the way you would implement that in Python. You would say replacement add if positive, and you say this is a subclass of Anger sim procedure, and then you define the run, say self is the class, and then A and B for these 2 parameters. You check if A is greater than B, or A is greater than 0, B is greater than 0, and return A plus B. So again, we can do the same thing with that string checking. But again, this thing has to handle symbolic values, not concrete ones. So this is actually what it looks like. Replacement check equals. You have an address to check and the length to check, and this is where that symbol resides, so wherever that string, encrypted string was. Then you do a load of whatever's there and say that's the user input string, and this is the string you want to check it against, and then you can symbolically evaluate whether or not you can get user input string to equal the check against string, and then symbolically return 1 or 0 to the engine as a result. And then you hook it by saying the check equals symbol is this, and then saying hook that symbol with this replacement check equals. And that's how you instantiate your sim procedure. Okay. And that's what this stuff describes. Sorry about that. Okay, I just wanted to show you this briefly. So this is the static binary level. You have all of these things that are now statically linked into your binary. And if you want to replace those with sim procedures that are from the Anger library, you can do something like this. hook at 8D10, which is basically, oh, that's not on there. Where's printf? Here is hook ED40, which is this call to printf. Hook that with the Anger sim procedure one. So that's how you would do it for a statically linked binary. Okay, so now we did all of that to do an automatic exploit generation. So this is, I'm only going to do the last level of this, the arbitrary jump. But the really high-level strategy is to first figure out the kind of exploit you want. Do you want a read exploit that reads an administrator's password? Do you want a write exploit that corrupts some system memory? Or do you want to do an arbitrary jump? So like a return, a buffer overflow followed by a return. And so after you figure out what you want, you write a Python function using Anger that figures out what are the conditions you're looking for that exploit. And then you ask Anger to solve for the input that will get you that exploit. So you constrain the system in a way to set up the attack, and then ask Anger to solve that for that input that executes those constraints. I'm going to skip arbitrary read, skip arbitrary write. These are levels that you can do in the CTF. It's all set up in the scaffold. You can read about it to figure it out. I'm going to do the arbitrary jump, which is the last level of the CTF. So to determine if we can find a buffer overflow so the idea here is that you control the stack. You can return to basically where the return address is, and if this is corrupted, you have basically an arbitrary jump. So you can check to see if the return address in memory of a function is unconstrained. So in particular, this green here, if this thing is unconstrained, then you have an exploit. But the problem with this approach is that you have a stack that has a whole bunch of return addresses, and they show up in any number of places, right? You can't predict where the return address necessarily is without doing a whole bunch of reverse engineering. So how do you set the thing up to look for an unconstrained instruction pointer? Well, you can basically ask Anger to flag when the instruction pointer is unconstrained and solve for inputs that meet that constraint. And that meets that thing. Okay. So, the places you will go with this. When the instruction pointer is unconstrained, there are basically an infinite number of possible branches. And typically when Anger gets this, it's like, I don't know what to do. I can't create 4 billion states for all the different addresses. So it'll actually, in normal cases, when it gets to an unconstrained instruction pointer, by default it's going to throw them away. To say, can't do that. But what you want to do is say, actually, I want that. I want the unconstrained instruction pointer. Moreover, I want that thing to point to code that I have in memory that I already placed, or I wanted that thing to return to a specific address, like the print good address. So that's the name of this. The name of the game for this level is like, hey, I want that binary to print good. I know the function that prints print good. I just need to constrain that instruction pointer. Whenever it gets to unconstrained, I want to constrain that to the address of print good and see if that actually gives me execution. So that's what we're doing. Okay. The high-level algorithm instruct Anger to save unconstrained states. While we haven't found a solution or exhaustively searched the binary, then for each unconstrained state, we can try and constrain the instruction pointer to be the instruction pointer that we want, the address that we want it to go to. And then we solve for the input. And then we keep on stepping active states until we either find an input that does this or the whole thing terminates. And then we know there isn't a buffer overflow attack on that binary. Okay, so the angry CTF levels on this. Here it is. So this is the vulnerable program. You see the read input has padding before this buffer, padding after this buffer, has a vulnerable scanf that does an unconstrained string read into this buffer. And the idea here is that you're going to overflow the return address of read input and then hopefully return to print good. And if you look at the program, it says enter the password, read input, and you're supposed to always print try again, right? This thing should not have an input that ever calls print good. All right? And in fact, you probably have to tell the compiler, you better not optimize the compiler, because then the compiler will say, oh yeah, print good's not going to be called, and it'll get rid of it. But yeah, in this case, the print good is there. You just need to figure out the address of print good. You need to find an unconstrained EIP, and then see if you can constrain it to that address. And that's what this automatic exploit thing is going to Okay. I will go straight to the level. So here is the big, the main parts of this. The first thing is when you start the simulation manager, when you instantiate it, you're going to say, hey, I'm going to start with a specific initial state that says save unconstrained to be true. I actually want to take those states and then look at them to see if I have an exploit. I'm going to have these stashes. So before I sort of, in the algorithm for generating these paths, we said there's an active state, there's a termination state. We're going to actually have the unconstrained state be a separate stash, and this is where Anger is going to store unconstrained states in its data structures. And then obviously there's a found state. So if an unconstrained state can be constrained to get the IP, the address to be print good, it's going to be moved into found. So that's just our data structure setup. And then while the simulation is active, or the simulation is unconstrained, and while we haven't found anything in our simulation, then loop forever. And then we check to see if there's anything in simulation.unconstrained. Because this means we have an unconstrained EIP. And then what we do is we set a variable EIP settable to be whether or not this EIP is equal to, so this is a constraint that we want to specify that says whether or not I can get EIP to be equal to the address of print good. So I didn't tell you this. Does it show up? Oh, I don't have the radar. Okay. So when you do the disassembly of this binary, you'll see that print good is actually at this address, and it looks like a ASCII codes because we wanted all of the passwords to be all ASCII. So you'll see with the interface that I have for my malware CTF, it needs to be all ASCII, printable ASCII, because I submit the input to a web form. So basically what I'm going to do is now I'm going to say, hey, I have an unconstrained state. I have a condition that I want to use to constrain it to something that I want. And then I say, is this satisfiable? So the method to use is to check if it's satisfiable, add the extra constraints that I want on EIP, which is this EIP settable. And then I'm going to, if it's satisfiable, then I'm going to move that state from unconstrained to found. Otherwise, I'm going to go and step the simulation. And whenever I have something that's found, it's going to return, and I'm going to have the exploit. Okay. So the other thing, so if I have the simulation found, I add the constraints in order to concretize the output. And then what I'm going to do is I'm going to add another constraint that says all of these have to be capital letters. So that's an additional constraint that we, as in our CTF, need for our web form. So Anger will give you everything, even the non-printable ASCIIs. So there's a whole bunch of inputs. In fact, there's an infinite number of inputs, not an infinite, but a huge number, like millions of inputs that will actually solve this level. And we wanted the ones that were all capital letters. And then we would, after adding those constraints, then we basically dump the output. And so the last thing I want to run is this thing. So this is the program. And when you run it against this binary that's got the buffer overflow, it gives you the exploit. It gives you this. And you can see, actually, print good. This is actually print good right in here, the ASCII for print good. So then if I copy that, this is the thing that blows up that buffer, and I print good job. So that's the heart of what they're using to get these things. They're doing something way more sophisticated in terms of pruning the input tree. Like, these are really simple examples. They're doing something more complex. That's it. Any questions? Yeah.
So if you weren't looking for exploits, but you were looking for doing QA and any unconstrained EIP would potentially be crashed.
Yeah, and actually, smart fuzzing will get that immediately. So what you do is you use something like AFL fuzz with address sanitization, and it captures any sort of pointers that go to uninitialized memory. That's what I would do for that, and that's why both of these things, when you use them together, they're really good for. That's why I think this is the future of testing, just because of the power it gives people to get rid of all these bugs. So they actually used AFL fuzz on libc, and they found like a huge number of bugs in Linux, and they're like, oh, we got to fix all of these. The other thing that happened was AFL fuzz was used to catch heartbleed in a minute. Like they were able to point that at OpenSSL and get that within a minute. It found that read overflow. So I think I didn't have any slides left. I might have a slide or two. No, that's pretty much it. So yeah.
Are you gonna post the slides?
I can put them. If you are interested in the slides, maybe just email me. Let me give you my email address. These are mostly Jake's slides, so ask him first. But yeah, I think it should be fine. All right, thanks for coming.